Welcome back to the Ground Up Podcast. Today we're diving into the invisible forces that hold up our world, or in some cases, bring it crashing down. If you've ever walked across a wet beach and noticed the sand turn white and dry around your foot, you've witnessed the complex relationship between soil and water. For decades, this relationship was a black box for engineers. They knew that adding weight to wet soil caused pressure to build up in the water trapped between the grains. But they didn't have a reliable way to measure exactly how much of that load the water was carrying versus the soil itself. Enter Sir Alec Skempton. In the mid-1950s, Skempton pulled back the curtain on this mystery by introducing his pore pressure coefficients, simply known as A and B. It was a breakthrough that shifted soil mechanics from an observational art to a precise science. He realized that soil isn't just a solid mass. It's a skeleton of minerals filled with voids. When you squeeze that skeleton, the water inside wants to push back. Skempton's genius was in quantifying that pushback through two distinct stages of loading, allowing us to predict soil behavior before the first shovel ever hits the dirt. The B parameter is the first gatekeeper. It measures how the pore pressure reacts when you squeeze the soil equally from all sides, like diving to the bottom of a pool. In a perfectly saturated soil, water is virtually incompressible compared to the soil skeleton. This means the B value hits a perfect 1.0, signaling that the water is shouldering the entire load. For engineers, this is the saturation check. If your B value is low, you have air bubbles in your soil, and your calculations for stability are going to be dangerously off base. But the real drama happens with the A parameter, which deals with shear. This kicks in when you start to deform the soil, pushing down harder on the top than on the sides. This is where the personality of the soil comes out. Some soils, like soft, sensitive clays, are prone to structural collapse. They shrink when sheared, causing the A value to skyrocket as the water pressure surges. On the flip side, dense sands or heavily compacted clays actually try to expand or dilate when you mess with them. This creates a vacuum effect, leading to a negative A value. Why should we care about these coefficients in 2026? Because they are the difference between a dam holding back a reservoir and a catastrophic mudslide. When the Teton Dam failed in 1976, or when we look at modern high-rise construction in coastal cities, the math tracing back to Skempton is what keeps the foundation secure. If we don't account for the A coefficient, a sudden load, like a new floor being added to a building, could cause the pore pressure to spike so high that the soil grains lose contact entirely, turning solid ground into a liquid nightmare. Skempton's work reminds us that in engineering, what you can't see is often more important than what you can. By giving us the tools to measure the silent pressure of water hidden deep underground, he gave us the confidence to build bigger, higher, and safer. So, the next time you look at a massive bridge or a skyscraper, think of the A and B coefficients working silently beneath the surface, balancing the weight of the world. Thanks for listening, and we'll see you in the next episode.